Hiya Pirates! Today what we're going to do is take a look at the idea of calorimetry. So what in the heck is calorimetry? Well, now we have spent a few days talking all about heat and specific heat capacity and mass and temperature change and all sorts of things like that. So we have a few terms that we are okay with, at least we should be at this point. And what we're going to do is we're going to be able to apply those terms and be able to solve some practical in-world problems. So a couple things. Thing number one, obviously we've talked about this guy before. A calorie is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. It is a number that we just made up as scientists. We just decided that water was going to be our substance of use. So we just decided that water is going to have a specific heat capacity of 1 as far as calories and grams and Celsius is concerned. So water has a specific heat capacity of 1. We're using water because it's nice and easy to work with. It's abundant. It's safe. It's not going to catch on fire or anything along those lines. We have a semi-infinite supply of it, and it is tremendously easy to work with. And so consequently, we have just decided that water has a value of 1. And because we have decided that water has a value of 1, we can figure out what every other substance is if we just compare it to water. Now, how are we going to do that? Well, we're going to need a very simple mathematical equation, which is then going to lead to some problems. So let me walk you through a few steps here. The first of which is the idea of the law of conservation of energy. And that is a very simple thing that says energy can't be created or destroyed. It can only be changed around into other forms. We see this oftentimes when we look at an automobile. We actually lose a great deal of energy in an automobile because we get chemical energy from the gasoline exploding in the engine pistons. But because of friction and all sorts of other aspects that go into a car, not a whole lot of that energy is actually used to move the car forward. We lose a lot of that energy, I guess, is a better way to say it. We lose a bunch of it in a variety of different areas, a variety of different places here. But having said that, even though that we, quote, lose that energy, we really didn't lose it. It's just that it's not particularly useful energy to us. Because again, energy can't be created or destroyed. It can only be moved or changed, I guess I should say, from one form to another. So, having said that, let's take a look at a couple of very simple examples and a couple of new terms. So first of all, if we were to look at this campfire is giving off heat, right? And so if we were looking at this campfire, because it's giving off heat, then we're going to call this an exothermic reaction. Exo meaning out. So that's a new term for us, right? If we look at this ice cube is going to sit on the counter and it's going to melt, and so the heat is going to go into the ice cube. So we're going to call it an endothermic reaction. Endo meaning in. And that's all well and good, except if you think about it over here, what if you were a person that was standing over here, right, with your very long neck? From your person's perspective, the heat is actually going in to you as a person. That's why you feel warm. So from your perspective as a person, you're actually endothermic over here, whereas the fire is exothermic. Or if we look at the ice cube, what if the air over here, that's what is losing the heat. So the air is actually exothermic, while the ice cube is endothermic. So it's really tough to tell in these thermodynamic situations, because for every situation where you lose heat, something else is going to gain that heat. So the fire is losing the heat, the person is gaining the heat. The ice cube is gaining the heat, endo, but it's coming from the air or the countertop, that's exo. So what we really need to do is we need to assign perspective. And there's a couple of new terms then that we need to establish. And those terms are system versus surroundings. So what is the system and what is the surroundings? Well, the system we're going to define, and forgive me here that this is silly, but it's really not. The system is going to be whatever we decide it to be. Basically, the system is whatever it is that we are interested in. So if we are interested in the fire, then the fire is our system, and everything else is going to be the surroundings. If we're interested in the ice cube, then we decide that the ice cube is our system, and everything else is the surroundings. So the system is whatever we decide it to be. The surroundings, then, is everything else. So, Halloween is upon us. Let's take a look at this example here. Now, what's going to happen here? What's going to happen is these kids are going to go up and they're going to get candy, right? And so the candy is going to go from the house to the kids. So, from the house's perspective, if we decide that to be the system, from the house's perspective, because the candy is going out from the house to the kids, from the house's perspective, it's exo. But if the kids are what we are interested in, if you're one of those kids, then you are endo candy because the candy is coming into you. So is it exo or is it endo? And the answer is yes, it's both. It all depends on your perspective. So from the perspective of the house, it's exo. From the perspective of the kids, it is endo. All right? Well, let's say that there were some houses that didn't really participate in the candy. So what happens to those houses on Halloween? Well, they get TP'd, right? So if you are the kids, right, and that's the system, the TP is going to go from the kids over here to the tree or to the property over here. So from the kids' perspective here, that's going to be exo toilet paper. And from the tree or the property's perspective, it's going to be endo toilet paper because the toilet paper is coming in. So once again, it all depends on your perspective here. And so when we do these thermodynamic problems, we have to establish, are we talking about this or that, the system or the surroundings? The system is whatever we decide to be interested in. The surroundings is everything else. So back up to our examples up here. Once again, I mentioned this before, but let's go ahead and look at it. This is an exothermic reaction from the perspective of the system, which is the campfire, if that's what I choose to be interested in. If this is my system, the ice cube, and that's what I choose to be interested in, well, then it's endothermic because I'm looking at it from the ice cube's perspective, and so the ice cube is gaining energy, so it's endothermic. So your system is whatever it is that you decide to be interested in. If your system is the house, then it's exo here, and the kids are endo. If the system is the trees, then it's endo here, and the kids are exo. It all depends on what you are interested in. So, new terms. System, whatever you decide to be interested in. Surroundings is everything else that's not the system. If it's an endothermic, then that means the heat leaves the surroundings and enters the system. If it's exothermic, that means the heat leaves the system and enters the surroundings. So again, endo and exothermic is system and surroundings. It all depends on your perspective here. So because we have defined this is my system and the heat is going in, it's endo. Because I have defined this is my system and the heat is going out, it is going to be exo from the perspective of the system. All right. So having said that, let's look at a very simple equation that's going to cause us lots of trouble. Now, our equation is simple. Heat lost equals heat gained. Because again, that goes back up here to our idea of the law of conservation of energy. Energy can't be created or destroyed. All it can do is change form. So if I have energy that is being lost, then whatever energy is lost is going to be the same amount of energy that is gained somewhere else. But that's going to cause us problems. All right, let's take a look at two guys here. Let me explain my idea here. Let's say that I've got Gary over here. And Gary starts off the day with no money in his bank account. All right? And here's Larry. And Larry, looking sharp in his suit, starts the day with $50 in his pocket. All right? Gary calls up Larry and says, "Hey, can you help me out? I need a little bit." So Larry decides to give or lose $20. Right? He decides to hand over $20. And that means that Gary over here is going to gain that $20. Right? But now let's look at their pockets. What's left in their pockets is that Larry has $30 and Gary has now $20. Or the change for Larry is that Larry's changed by negative $20 and Gary's went up by $20. Hey guys, does $20 equal negative $20? It does not. So this equation of heat lost equals heat gained doesn't work because Larry overall, again, if I just summarize what's going on here, do this again. Larry, what happened to him is that he lost $20 in this example, and Gary gained $20 in this example, and negative 20 does not equal positive 20. Mathematically, it does not work. And the reason that it doesn't work is because the negative sign is being implied through these words that are here, and it is not mathematically functioning properly. So how do we fix it? Well, all we have to do is take this negative and turn it to a positive, or take this positive and turn it to a negative. So what we're going to do is we're going to change our equation. Instead of saying heat lost equals heat gained, we're going to say heat lost equals negative heat gained. So if that's the case, now then what I'm going to do is I'm going to take this negative 20 and I'm going to set it equal here to negative positive 20. Negative of a positive is going to turn into a negative, and now all of a sudden it works. So if you didn't follow that, let me make it easy for you. Heat lost does not equal heat gained. Heat lost equals negative heat gained. We have to include a negative sign for this to work. Or, to put it another way, Q of the system, Q being heat, is going to be equal to negative Q of the surroundings, or Q lost here is going to be equal to negative Q gained. So that's our equation that we're going to use to mathematically figure all of these things. Q lost is going to be equal to negative Q gained, because if not, the math won't work out properly on this. All right. But remember, in our last section, we saw that Q is equal to MC delta T, right? MC times TF minus TI. So if I substitute MC TF minus TI in for these guys here, all of a sudden, guys, our very simple equation of heat lost equals heat gained has now turned into this equation here. Ooh, goodness, look at that. Don't be afraid, though. This is MC TF minus TI. That's just Q. And this is also MC TF minus TI. And this is also just Q with our negative sign in there. So MC TF minus TI that's lost is going to be equal to negative MC TF minus TI of whatever is gained here. So what we're going to be able to do with this very complicated looking equation is we're going to be able to solve a whole bunch of problems for this if we know that equation there. MC TF minus TI lost equals negative MC TF minus TI gained. So that's the super important one there, that guy right there. Make sure that you write that one down. We're about to use it a bunch. All right, so what we're going to do is we're going to get out our calorimeters, which are just styrofoam cups, and we're going to assume that no heat is lost to the environment. We have a perfect system, and we're going to be able to solve some problems. What kind of problems? Well, let's check it out. Let's say that I take 100 grams of hot water at 80 degrees Celsius, and I mix it with 100 grams of cold water at 20 degrees Celsius. What's going to happen when it's all done? What is going to be the final temperature? What's going to be TF, the final temperature that's in that cup when hot water is mixed with cold water? Now, if you're very intuitive, you might look at this and go, I think I know what the answer is. It's going to be right in between the 80 and the 20. I'm just going to average them out. And 80 and 20, the average of those two guys is going to be 50 degrees Celsius. So if you're intuitive about these things, you might just be able to figure out the answer just by kind of looking at the numbers. Now, this only works because I have 100 grams of hot water and 100 grams of cold water. And it's water, which means its specific heat capacity of 1. And this is also water, so its specific heat capacity is 1. So I have equal amounts of the same substance. Yeah, the hot's going to get cold, the cold's going to get hot, and we're going to be able to figure it out from there. Now, if you're not intuitive like that, then what we're going to have to do is we're going to have to use our equation here. MC TF minus TI lost equals negative MC TF minus TI gained. So let's take a look here. I want to know what the final temperature is going to be here. That's what I'm interested in. So my equation is going to be the mass times the specific heat capacity times the final minus the initial temperature of the hot water. That's what's going to be lost, right? So MC TF minus TI of my hot is going to be equal to negative MC TF minus TI of whatever is gained over here by the cold water. So, what do I know? I know that for my hot water, I have 100 grams, so I'm going to plug that in. I know that it's water, so I know that its specific heat capacity is 1 calorie per gram degree Celsius. Now, I don't know what the final temperature is, but I do know that the initial temperature is 80 degrees Celsius. And now that's going to be equaled over here, where again I have 100 grams. And then this is going to be 1 calorie per gram degree Celsius because I have 100 and I have 1 for M and C. Again, M and C. I don't know what the final temperature is going to be, but I know that my initial temperature is 20 degrees Celsius. So, using algebra, let's now solve this. So this is 100 times 1, so that's going to be 100, times TF minus 80 is going to be equal to negative 100 times 1, so that's 100, times TF minus 20. Now, what most of you will probably do at this point is distribute, and that's fine. So that's going to be 100 times TF minus 8,000 if I distribute here and here. And most of you will probably want to distribute over here, and I'm okay with that. So again, this negative 100 goes here, and so that then is going to end up being negative 100 TF plus 2,000. Now, in order to solve for this, I have TFs on this side and TFs on this side, so I got to get those two together. So I'm going to add 100 TF over here, which is going to add 100 TF over here. So now I'm going to have 200 TF minus 8,000 is going to be equal to 2,000. Now I've got to get this 8,000 over there. And again, this is just algebra, folks. So then that goes away. And then 8,000 and 2,000 is 10,000. And now I have 200 TF is equal to 10,000. I'm going to divide by 200 and divide by 200. And my TF, sure enough, is 50 degrees Celsius, exactly like I thought at the start of this. But I've just kind of proved it. So, if you know your initial conditions between two things that you are going to be mixing, you can figure out how much one is going to lose and how much one is going to gain, and then therefore you can figure out some factor that is involved between them. Let's do one more example. So this says, what would be the final temperature if 40 grams of water at 10 degrees Celsius is mixed with 75 grams of water at 90 degrees Celsius? Now, if this one you tried it and tried to do 10 plus 90 divided by 2 is going to be 50, you're not going to work, because even though we have the same substance, water and water, I have 75 grams of hot water, but I only have 40 grams of cold water, so it's not going to work out. So what do I do? Well, you simply plug into your equation and do the complicated algebra. So what is your equation? Your equation is MC TF minus TI of the hot is going to be equal to negative MC TF minus TI of the cold. All right, let's plug our numbers in. Here's our hot. I'll put it in red. Hot here, 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 and here. So how much hot water do I have? I apparently have 75 grams. My specific heat capacity is 1. I don't know my final temperature. If you'd prefer, I'll call it X. But I know that I started at 90. And then I'm going to have to come in over here and do negative for the cold. But the cold are these numbers. So if I've only got 40 grams of the cold, its specific heat capacity is still 1. I still don't know what the final temperature is, but I know when the hot and the cold mix, they're going to be the same somewhere in between. And then I'm going to subtract 10 from that over here. So this is going to end up being 75 times x minus 90 is equal to negative 40 times x minus 10 once you combine and distribute. So now I'm going to go ahead and distribute here and here, and I'm going to go ahead and distribute here and here. And when I do, I'm going to end up with 75x minus 6,750 is going to be equal to negative 40x plus 400. Now again, I've got to get these x's in Texas all on the same side. I like positive numbers. So I'm going to go ahead and add 40x to the right. And if I do that, I'm going to have to add 40x to the left in order to keep things the same. So that's going to get me 115 x minus 6750 is equal to 400. Now I have to add 6750 to this in order to get rid of him. So that's going to be 115x is equal to 150, which then means that my x, if I do the math on this properly, 7150 divided by 115 is equal to about 62 degrees Celsius. So that is how you do these problems. You use this equation, which looks complicated, MCTF minus TI is equal to negative MCTF minus TI, for your hot that you lost and the cold that you gained.